Hi, my name is Francesca and I'm an academic tutor. I tutor a variety of topics, including math, chemistry, paper editing, and standardized tests. So chemistry is just one of the many topics that I tutor, and I'm a graduate of UC Berkeley. I'd like to present a couple different problems to you from a typical chemistry class, whether it be from high school or from college. I thought I would just start out with something really easy, nomenclature, which is something that any student would have to know for a basic chemistry class. So I thought I would start out with Na2CO3. This is just a pretty simple ionic compound. The Na has a plus charge while the CO3 has a negative charge, which is what comprises an ionic bond. The positive combining with the negative to like equalize the charge. So the ionic bond is basically defined by an attraction of two opposite charges, and it's the strongest kind of bond. So in order to name this compound, I would first want to look up the name for Na. It's just sodium. The name for CO3, however, is carbonate. It's considered a polyatomic ion because a number of different elements, which would be carbon and oxygen, are actually combining together to form a negative ion. So this entire portion here is the polyatomic ion. So we have sodium combining with carbonate, and that's actually just the name of the entire compound, sodium carbonate. I don't have to actually write out a prefix for either one of them because it's an ionic bond, so you can actually discern how many of them you would need just from the name sodium carbonate because of the charges. Whereas with something covalent in nature, like this compound, which is constituted by elements that are coming from the right side of the periodic table. They're combining in a bond that's defined by sharing of electrons rather than the attraction of two opposite forces. So with this one, you actually do need to use prefixes, whereas for this one, you don't. The prefixes for this one would be tetra for the 4 here, and then deca here. So the name for this compound would be tetra phosphorus, and then dec oxide. I'll write the dec. So that's the name of this compound, tetraphosphorus, just the name of this, and dec oxide, because you have 10 of the oxygens. Whereas for this one, it was named using the ionic system, which is not involving prefixes. You just have to list the names of the elements, so sodium carbonate. In the next one, it's the third special case. Basically, nomenclature is just made up of 3 different cases: the ionic bonds, the covalent bonds, and then under the ionic subgroup, there would be a subgroup of transition elements that have 2 or sometimes even 3 different charges, depending on what they're combining with. In this compound here, this would actually be named as Fe3. So you'd have to name it as iron 3 and then oxygen, because again, you don't need to use a prefix on the oxygen just because it's in an ionic bond. But you do have to state the number of the Fe just because there's 2 different forms of iron. There's iron 2 and there's also iron 3. This is the variety that has the +3 charge, whereas the oxygen has a -2 charge. So negative 2 times 3 is negative 6. Positive 3 times 2 is positive 6. And that's why this is a balanced compound, because the positive charge is balancing out the negative charge. The next topic I'm going to discuss is converting 150 grams of that same compound, iron 3 oxide rather, into moles. What you need to do for this is just write out a simple formula here, just using the molecular mass of iron oxide, which is 168 grams. So you can look that up actually on your periodic table to get the molecular mass. You would want to take iron, which is 56 grams per mole. You're going to multiply that by 2. And then the molecular mass of oxygen is 16. You have 3 of them. Multiply that by 3 to get 48. So then if you add up those two numbers, you're going to get 168 grams per mole. So that's the molecular mass of Fe2O3. So then we go about multiplying 150 grams times 1 mole over 168 grams. This will actually equal out 0.89 moles. So here we have it, 150 grams times 1 mole over 168 grams, it equals 0.89 moles. Notice that the units from the grams cancel out, and then you end up having moles in your answer. So that's the basic system for going from the mass of a given substance into the moles of that substance. Moles are considered much more applicable for determining products and for a given reaction, and for also using stoichiometry. And stoichiometry is the next topic that I'd like to present here. Here is the basic reaction that we're going to have. So we're first going to have to balance out the reaction before jumping into stoichiometry. This is actually another topic that's covered in most chemistry courses. You need to have the number of moles that you're starting out with equal the number of moles on the product side. So number of moles for reactants has to equal number of moles for reactants for any given element. So if we have 12 carbons here, then we must have 12 here. That would be the first step for balancing this reaction. Then we can count up how many hydrogens we have. We have 22 here, whereas we only have 2 here. So we can just multiply that by 11. 11 times 2 is 22. We had the 22 here. So now we have an equivalent number of hydrogens on the right and left hand side. Now the oxygens would be a little bit more complex, because we have 11 of them here, and we have 2 here, which would create a total sum of 13. Whereas here we have 11, and then we have 12 times 2, which is 24. So we need this side to equal the other side. So 24 plus 11, there you have 35. We need this side to also equal 35. But we also have 11 right here. So basically we need to have 24 oxygens here plus the 11 to equal the 35 oxygens of this side. So here, if I put a 12, that would actually solve the problem. 12 times 2, 24, plus 11 equaling 35 oxygens. 12 times 2, again, we have the 24 here, 11 here. Now it's completely balanced. Now I have a system of solving the original question, which is if you have 10 grams of C12H22O11 and 10 grams of oxygen gas, how much CO2 will be produced from that reaction? So the first step would be to convert 10 grams into moles, and I already did that using the molecular mass of 342 grams. So I would want to take 10 grams of that substance over 1 mole, times 1 mole over 342 grams, and that actually equals 0.029 moles. Then I would want to do exactly the same thing for oxygen. If you do that, you'll actually get 0.3125 moles. You're taking 10 grams times 1 over 36 grams, and that's what gives you the 0.3125 moles. So we end up with these two different numbers. This would be the number of moles for the C12H22O11, and then this is the number of moles for the oxygen gas. Now I'm going to create a stoichiometry chart that reiterates the same concept that I was just writing on the other sheet. I'm going to write out the original equation in its balanced form. If it's not balanced, then it won't work. So now here is the equation, and I have to bring down the actual molar ratio. So the molar ratio would be 1 mole of this substance to 12 moles of this substance to 12 to 11. And I'm going to write it in terms of x. 1x, 12x, 12x, and 11x. So there we have it. That's the molar ratio of all of the substances in the problem. At this point, I'm going to want to actually write out the name of this substance again. And then I write down the number of moles of that substance where the substance meets itself, which would be right here. So 0.3125. Then I look at what x lies above that number. It's 1x. So if 1x equals 0.3125, then I have to multiply 0.3125 times 12. So that would be the answer for that portion. 0.3125 times 12 actually equals 3.75. And then if this is 12x, then this must also be the same number because this is also a 12x. So I'm going to write 3.75 once again. Then I'm going to take that same number, 0.3125, times 11 to get 11x, and that number actually equals 3.438. So now I have taken the molar ratio given 10 grams of this substance, and I've determined how much oxygen I would need to completely react with that substance, and then how much product would be obtained. It would be 3.75 moles of carbon dioxide and 3.438 moles of water. Now I need to determine how much product would be obtained using the 10 grams of oxygen. So I'm going to write O2 here. I'm going to convert it, well, actually I already did that. I'm going to write the number of moles that I have, which is 0.3125. Oh, I'm very sorry. I actually wrote this in the wrong spot. This would be for if I had 0.3125 moles of this substance. I'm going to just pick a different number of moles than for oxygen. I'll say that I started out with 35 grams of oxygen instead. That would mean that I have 0.97 moles here. This entire chart, by the way, is 4 moles. If I have the 0.97 moles here, then this is actually now going to equal the 12x that lies above it. So 1x no longer equals 0.3125. 0.97 equals the 12x. So if 0.97 equals 12x, then we want to divide that by 12 to obtain 1x, which would be 0.08. Then I can transfer that same number over here. 12x is still going to be the same. It'll be 0.97. Now for 11x, I'm going to just want to take the 1x, which was 0.08, and then I'm going to multiply that number times 11. That actually equals 0.89. From here, you're at your home stretch. If you have this number of moles of this substance and this number of moles of this substance, then you pick the lower, the row containing the lower number of values, and that's your limiting reactant. This clearly has the lower number of values all across the board. 0.08 is lower than 0.3125, so then you can label this as your limiting reactant. It's limiting the amount of product that you can have, while the other substance would be in excess. So this would indicate the number of moles of product that will be obtained. So that's all I have to show for chemistry. Again, my name is Francesca, and I've been doing this for several years now. I've been tutoring primarily math and chemistry, and I've been also doing some paper editing. So I can tutor for standardized tests, such as the SAT. There's also the SAT-2 chemistry portion. I can tutor for that. I went to UC Berkeley for 4.5 years. My first 1.5 years was spent in the pre-medical field, and that's where I acquired my knowledge for chemistry as well as math. I had to take 3 semesters of chemistry and 2 semesters of math during that time. Also, I've been tutoring a huge diversity of students, ranging from really young ages to, middle-aged or so. Pretty much I can tutor chemistry at a college or high school level, and you can keep on looking at iSchools for updates on new videos that might be coming out for my tutoring services. If you'd like to contact me, you can call me at 510-689-7654, and my email address is info@learningexperience.us. My website is www.learningexperience.us. I hope to hear from you soon. Bye-bye.